Hey guys, I am Gautam from IIT Kharagpur and welcome to Easy. In this video, I am going to talk about one most important topic, that is Jahn-Taller distortion. Okay, so first I will tell about the Jahn-Taller distortion, the basic theorem, and I will explain some terms, some topics, some points, and then finally I will elaborate the whole things. Okay, so keep watching. So first, what is Jahn-Taller distortion? So what is the statement? So the statement is, in an electronically degenerate state, a nonlinear molecule undergoes distortion to remove the degeneracy by lowering the symmetry and finally by lowering the energy. Okay, so let's elaborate different points from this statement. So the first point is, what is electronically degenerate state? Okay, so actually electronically degenerate state is all about the system which are in the same energy. So degenerate state means the state or the system which has the same energy. So let's take an example. Say this is 5d orbitals. This is d x y y z z x x square minus y square z square. So here without any field, not any octahedral field, not any tetrahedral field, just for a free ion, if the electronic configuration ends with d or the valence electron is d, then for that ion the d orbital, for that free ion the d orbital is totally degenerate. That means every orbital x y y z z x x square minus y square and z square, all those orbitals are in the same energy levels. Okay, so if one electron present right here, then what will be the degeneracy of that electron of that system? So the degeneracy will be total 5. How? This electron may be like here, or like here, here, and also here. So this electron can move throughout the system and the energy of the system will be same. Okay, because all the energy levels, all the d orbitals are have same energy. Okay, so that is why it has total its degeneracy is 5. Okay, so if we take this kind of system d2 system, then you can easily calculate the degeneracy. Okay, so just calculate and let me know in the comment below. Okay, so let's take another example. So when 5d orbitals and these 5d orbitals are in free ion. Okay, so when this is in the octahedral field, that is it will split into Eg and T2G levels. Eg level consists of dx square minus y square and dz square orbitals, and T2G consists of dxy, dyz and dzx orbitals. Okay, so now if one electron is present in the T2G level, then what will be the degeneracy of that system? So now you cannot consider Eg level as this T2G level, that is xy, yz, zx orbital. These levels don't have the same energy as dx square minus y square and z square. Okay, so that is why you just need to compare the degeneracy, or you just need to calculate the degeneracy in this T2G state. So here up spin, then if this electron can be right, say this electron is in the dxy orbital. Okay, so dxy level, then this electron can be right on the in the tyz level and also dxz level. So here the degeneracy is 3. Okay, so say this electron, so say one electron is in the Eg level, that is say it is in the dx square minus y square orbital or level. So the degeneracy here will be what? 2. Okay, because this electron can present in the dx square orbital, dx square minus y square orbital or dz square orbital. Okay, so that is why the degeneracy is 2. So this is all about the degeneracy. Okay, now coming to another point from the statement, that is a non-linear molecule. So why for linear molecule JT distortion isn't possible? Because say a linear molecule, the linear, for formation of a linear molecule, the orbitals should be linear, and if a field works from this direction or this direction or this direction, then these two, all the linear orbitals will face the same interaction, and that is why, or if their energy will be decreased or energy will be increased, both can be possible, and that is why the degeneracy will be same. So of course you have to lower the degeneracy to make stable the system. Okay, so that their degeneracy will not change. So that is why you have to consider nonlinear molecule for JT distortion or Jahn-Taller distortion. I am shorting it out as JT distortion. Okay. So next, coming to another point, that is removal of degeneracy. So why removal of degeneracy is necessary? So actually removal of degeneracy means, actually I have already seen that if one electron is present in the free ion, free d orbital, then its degeneracy is 5. And then in the octahedral field, if that electron is present in the T2G level, its degeneracy is 3. And if, say, it is not possible, but say if electron present in EZ level, its degeneracy will be 2. So here degeneracy is 5, here degeneracy is 3. So that's how the degeneracy decreases, or this is all about the removal of degeneracy. Degeneracy is removed by 2 units. So this is the removal of degeneracy. Okay, so now coming to another point, that is lowering of symmetry. So what is lowering of symmetry? What does this mean? So say let us take an example from organic chemistry. It will help you to understand what is lowering of symmetry and how it helps to make a system stable. So take another one example from, that is cyclooctatetraene. Okay, you have seen that molecule, but it is not stable in like this. It is not planar. The planar system will not be stable. So how it looks like? It will be stable when this system is like this. Okay, and the electron pi orbitals, pi bonds are like this. So this is stable. This is a tub-like structure, and this is planar. So this is not stable, but this is mostly symmetric. It is a 8-fold degenerate system, but 8-fold degenerate system, but it is a 4-fold degenerate system. That is why, as it is a 8-fold degenerate system, it is more symmetric, and it is a 4-fold degenerate system, and that's why it is less symmetric. So actually this molecule is much more stable than this one. Okay, so here how you can see that the removal of degeneracy, that is 4 units here, makes the system very stable. Okay, so let's elaborate these things taking an normal example. Say a system has 10 symmetric axis of symmetry, and that system, after rearrangement, any kind of rearrangement, it has 5 or 6 axis of symmetry. So this will be much more stable than this, and this forms by lowering the number of symmetry or lowering the symmetry, and that is why removal of degeneracy and lowering of symmetry makes the system much more stable than the previous one. Okay, so this is all about the 4 or 5 points about the statement, and then coming for elaboration. Okay, so let's elaborate all those things. And here I want to say something, that I will say you another statement about Jahn-Taller distortion. So just keep watching, and that will help you to determine that which system shows JT distortion and which doesn't. Okay, so Jahn-Taller distortion is actually 2 types. One, Z out distortion, and second is Z in distortion. So what are these? So let's first elaborate about Z out distortion. So let's take an example. It will help you a lot. So say a system like CuH2O6 2+. This is a D9 weak field ligand, that is high spin system, or maybe high spin or low spin, doesn't matter. Okay, so D9 system, it looks like this. This is T2G, this is EG. So 1 2 3 4 5 6 7 8 9. It will be like this. Maybe it will be high spin or low spin. The configuration will be same. Okay, so now these two orbitals, this orbital is totally symmetric, so symmetric orbitals are not allowed to show any distortion. So distortion will depend on only on the dx square minus y square and dz square orbitals. Okay, so say this is dz square orbitals, and this is dx square minus y square orbital. Okay, so if this configuration like this, okay, so if the electronic configuration looks like this, that is, I am considering that the 9th electron will be fulfilled in the dz square orbital, not in the dx square minus y square orbital. It may go to the dx square minus y square orbital, but because these two orbitals are degenerate, so I am considering here that the ninth electron will go to the dz square orbital. Okay, now let's elaborate this by drawing the picture. Let's say the Cu atom is like here, and this is x-axis, this is towards the y-axis, and this is towards the z-axis. So this is all about the four axis, all about those axes. Okay, so now let's take I am considering Z out distortion. Okay, so what about Z out distortion? When Z out distortion is occurred, so if electron configuration will be like this, that is the the number of electron in the Z square orbital is greater than the dx square minus y square orbital. Okay, so what will happen if more number of electrons are present in the dz square orbital? So repulsion will occur in this orbital, that is the axial bonds. Okay, so here all those ligands are connected. Okay, and if dz square orbital is fulfilled by more number of electrons than dx square minus y square, then repulsion will occur in those orbital, that is in the z axis orbital. Okay, and that is why these all ligands will be fixed in these positions. But due to negative charge repulsion in the dz square orbital, the axial bond, this is the axial bond, axial bond length will increase, and that is why it will show Z out. Z out means the Z orbital goes towards the out. Okay, out means it will increase the bond length, the axial bond length. Okay, and that's why I am telling this as Z out distortion. So why distortion? Because all the bond lengths are not same now after distortion, and that is why it is distortion. And Z out because Z axis are towards the out of those central metal ion. Okay, so that's why it is Z out. So now coming to Z in distortion. So Z in is all about the opposite one. So if the configuration is like this, this is dz square, this is dx square minus y square. See, if electron configuration is like this, so here also more repulsion in dx square minus y square system. So that is why, of course, similar as the previous one, this bond length, more electron, there is more repulsion in case of dx square minus y square orbitals. So that is why this system, for this system, the dx square minus y square, that is dx and dy directed ligands or directed bonds, bond length will increase more than the ligands towards the dz square orbital or towards the axial bond. Okay, so the planar bond length will increase than the axial bond. That is why if a system looks like this, previous it is looking like this one, this all bond lengths are same, and after increasing all bond lengths, it will be like this one, and these two bond lengths are same as previous. These two bond lengths are same, as there is no repulsion for these two bond. So this will be like this. So that is why actually here the z-axis bond length doesn't change. So what happens? Actually the bond length of the x and y-axis bonds are increased. That is why it looks like that the bond length decreases of the z or axial system, axial bonds. Okay, that is why it is called the Z-in. Actually Z-in means maybe you may think that the length of the axial bonds decreases, but not that one, because here these bond lengths increases, and that's why it looks like that actually the axial bond length decreases, but it is not true. Okay, due to increment of these x and y directed ligands, x and y directed bond lengths, this kind of Z-in distortion occurs. Okay, so now I will tell about some important point about Z-in and Z-out distortion, and I will give you some example. So Z-out distortion will be seen when electron will present in the dz square system, or a system in which z axis is involved. Okay, and Z-in distortion will be occurred when electrons are present in the x and y axis orbitals, that is dx square minus y square and dxy. And for Z out, electrons when are present in dz square or dxz or dyz. But theoretically, this is not quite true. Okay, so you just may think if you face any questions from these, then you can apply these things to answer those questions. But this is not theoretically absolutely true. Okay, so it's just a trick, you may say. Actually, in most of the cases, this kind of things are seen, and that is why this is important. Okay, any electrons remains in these levels, then it will show that the system will show the Z out type distortion. And for if electrons are present in this system, then it will show the Z in distortion. Say D1 system. For D1 system, if the first electron present in the dxy orbital, then the system will show Z in distortion. And in similar case, if a system that is say D2, then say of course say first electron is in the dxy level and the second electron of course will be dyz or zx in the T2g level. Then of course the system, as the system involves dxz or yz, that is z orbital, z axis, thus the system will show Z out type distortion. Okay, so here I have already showed you about this example, CuH2O6 plus. I have considered this example because this is a very important example. So just remember this one. Okay, so the system which contains this kind of orbital electron distribution shows Z out, and the system which contains this type of orbital electron distribution shows Z in type of distortion. Okay, so let's take other examples. Like for Z out distortion, the examples are here: D2, then D4 high spin, then D7 low spin, then D8 low spin, and finally D9. Okay, so actually I have shown already the Cu copper CuH2O6 plus example for D9. Okay, so this will show Z out distortion, and Z in, remember, D1. It will be the most easy example for Z in distortion. Okay, so I am telling you again and again, but you cannot consider by seeing an molecule that it will show Z in or Z out type of distortion. But it is the shortcut if you face this kind of question to answer. Okay, and I want to add something, that if the degeneracy occurs, degeneracy means the system is symmetric. That is, suppose this is T2G state. If it is the D3 system, then it will not show any kind of distortion because it is totally symmetric. So to show distortion, it should be asymmetric. Okay, and the asymmetric example, say for T2G, this may be D1, this may be D2, this may be D4, this may be D5, but not D6. D6 will be totally symmetric. Symmetric means the system is totally fulfilled or half filled here. Okay, similar case is true for EG level. For EG level, for one electron, this is asymmetric. For 2 electron, this is symmetric. 3 electron asymmetric. 4 electron symmetric. So remember that any orbital which has symmetric electronic configuration will not show any kind of distortion. So it should be asymmetric to show any kind of Jahn-Taller distortion. Okay, so now let's say one thing, that if a system, another point you should remember this point also, that the asymmetric factor is shown in the EG level, that consists of dz square and dx square minus y square. Okay, then this kind of system, if degeneracy is present in dx square minus y square or dz square system, the z square orbital, then this type of systems, that is, I have shown you the D9 system of copper Cu2 plus complex. Okay, so this kind of system will show much more Jahn-Taller distortion. But if degeneracy is present in dxy or dyz or dzx orbital, then the distortion factor, that is Jahn-Taller distortion, will not be that much effective, because these orbitals, if any ligand is for octahedral case, the ligands come generally towards the dx square minus y square orbital or dz square orbital, not towards the dxy or dyz or dzx orbital. So these orbitals don't point towards the ligand. Okay, so that is why these orbital doesn't affect the distortion that much. So similarly, the tetrahedral system, which generally consists of this kind of orbitals, the orbitals pointed to the ligands by this kind of orbitals. That is why the Jahn-Taller distortion is not that much effective in tetrahedral system. Okay, but if any kind of asymmetricity or asymmetric systems or asymmetric orbitals, asymmetric electronic configurations are present, then the tetrahedral system also shows the Jahn-Taller distortion, but the distortion effect is very low over there. Okay, so now coming to the splitting of orbitals after distortion. So what happens after distortion in the splitting pattern? So let's first take the octahedral one. So this is octahedral system, and this total splitting, sorry, it will be 2 orbital, and this is 3 orbital. This is T2G and this is EG. This is consist of XY, YZ. I am not writing D, and ZX, and this is all about x square minus y square and z square. Okay, so after distortion, if say I am trying to split the system taking D9 system. Okay, so for copper 2 plus system, say dx square minus y square, this one, and this one d z square. If the electronic configuration is like this, okay, so what will happen? This will of course show Z in distortion, as I have already shown you. So for d x square minus y square orbital, there are one more electron than d z square, and that is why so more repulsion will occur for dx square minus y square system, and that is why the bond length will increase. And after increment of this bond length, what will happen? Finally, the system will be like this. So if the bond length increase, then finally the system will be stable, and if the system becomes stable, then the energy of the dx square minus y square orbital of course decreases, because after increment of this bond length, of course this system, the orbital of the directed orbital towards the ligand of dx square minus y square, of course the energy of the system decreases, because the stability also increases. And that is why the EG level that consists of x square minus y square and z square orbital will be splitted like this. This will be the energy of the dx square minus y square orbital will decrease because of the increment of this bond length. So this will be like this one, and this will, and from the centrosymmetric rule, the energy of this dz square orbital will increase in the similar amount. Okay, so now let's take, if the dx square minus y square system, the energy decreases, that is the system becomes more stable, then of course the similar effect will show the dxy orbital, and as dyz and dzx consists of z orbital, so that is why these two dxz and dyz, so that is why as these two consist of z orbital, so that is why their energy will be increased in the similar amount. Okay, so this is the splitting after Z in distortion, Z in. Okay, so and what about the Z out distortion? So Z out distortion will be opposite of this one. So for Z out distortion, the electronic configuration will not be like this. So this electron will be right here. So more repulsion, then more increment of the bond length, that is axial bond length, the Z axis bond length, and then after the increase of the bond length, the system will be stabilized, and the dz square orbital will be stabilized. Okay, and that is why what happened? The energy decreases of the dz square orbital, and the similar amount of energy increases for the dx square minus y square because of the symmetry rule. Okay, similarly the energy of the dyz and zx will decrease, and for dx square minus xy orbital, the energy will increase in a similar amount. Okay, so this is all about the Z out distortion. So for Z out, this is the splitting. For Z in, this is the splitting. Okay, so I hope you understand all these things. And here one thing is another point is important, that is static and dynamic Jahn-Taller distortion. This is also very important. Okay, so let's check out this topic. So there is static and this is dynamic Jahn-Taller distortion. Static ZT distortion, dynamic ZT distortion. Okay, so what is static ZT distortion? So just let's differentiate both of them. So I am adding some point first. For static Jahn-Taller distortion, you will see the degeneracy in the EG level, that is dx square minus y square and dz square orbitals levels. Okay, so and for dynamic Jahn-Taller distribution, the degeneracy you will notice that in the degeneracy will be shown in the T2G level, T2G level. Okay, that is dxy, yz and zx level. Okay, so this is the first point. And what is, now let's discuss about the static. What is static? So static means the distortion is permanent. Jahn-Taller distribution, so distortion will occur and the distortion is permanent. So when this kind of distortion is shown, system like CuH2O whole 6 2 plus. This system, that is D9 system, of course degeneracy is shown in the dz square and dx square minus y square orbital, and finally it is in the easy level. So degeneracy in easy level for CuH2 whole 6, this you can see as Z out distortion. Okay, as most of the cases the Z out distortion is preferred. Okay, so as most of the cases, not this is I am not telling this from anywhere, because I have already said you that you cannot imagine this or you cannot explain theoretically. Okay, so it's Z out distortion, and Z out distortion is fixed and it is permanent. Okay, so that is why it shows the static Jahn-Taller distortion. Okay, and that is why the bond length, so for CuH2O6, if Z out type of distortion occurs, so the axial bond length is greater than the other 4 bond length. Okay, that is why the axial bond length is always greater. It doesn't change with if we vary the temperature of the system. Okay, but in case of dynamic Jahn-Taller distortion, if we change the temperature of a system, then the bond length or other thing, of course bond length, or that you may say that distortion will change. Distortion of the system will vary. Okay, so how? Let's take an example like this kind of system, FeH2O whole 6 2 plus, and this is weak field ligand, that is Fe is 2 plus. This is D6 high spin system. So as this is high spin system, so the configuration will be T2G4 is G2, and the degeneracy is you can see the degeneracy in the T2G level. So I have already said you that degeneracy in the T2G level will show the dynamic Jahn-Taller distortion. Okay, so at lower temperature you can see the bond length is same, but if you increase the temperature you may see that the bond length is not same if we increase the temperature. So that is why it shows the dynamic Jahn-Taller distortion. Okay, so now let's take another example like this kind of example, M2 PB Cu NO2 whole 6. I am giving you this kind of complex example because I have seen this example in a lot of books. Okay, so that is why this may be important. Okay, so here M is equals to, M can vary, potassium, rubidium, cesium and finally thallium. Okay, so for these systems M may be any one of these. Okay, so for this system at low temperature the distortion is the system is tetragonal, and at high temperature the system is octahedral. So low temperature tetragonal, high temperature octahedral. So the system varies its structure when we change the temperature. Okay, so that is why this system shows the dynamic Jahn-Taller distortion, because at low temperature it shows one distortion, at high temperature it shows another distortion or another structure. Okay, so after distortion structure may change, so distortion is present right here. Okay, so this is all about these two types, static and dynamic distortion. Okay, so now I have already said you that I will say another statement that shows. Okay, so you can see the statement on your screen that in a nonlinear molecule, if degenerate orbitals are asymmetrically occupied, a distortion will occur to remove the degeneracy. So you know all these things. So here it says that if any system consists of asymmetry, okay, so if there is asymmetry, and you can easily imagine that the system will have the Jahn-Taller distortion. Asymmetry means the degeneracy in the T2G level and easy level. Okay, or easy level. So if the degeneracy present in case of easy level, the distortion will be greater, and for T2G level the distortion will be less, but it will show the distortion. Okay, so just in JAM 2017 there was a question, I don't remember, but there's a question that which system shows the degeneracy. So you have just find the system which has the asymmetricity. Asymmetricity means suppose a system that is D1 for T2G orbital, D1 is shows asymmetry, it is asymmetric. D3 is not asymmetric, this is totally symmetric because you cannot find any degeneracy from over here, right? So for D4, these orbital, this electron, fourth electron may be right here or right here, so it has degeneracy 3. Okay, so here if a system has degeneracy or if a system shows asymmetric electronic distribution, then the system will show the Jahn-Taller distortion. It is true for octahedral, for tetrahedral system. Okay, so just remember these ones. So to find degeneracy, just see the system and then find the degeneracy or the asymmetricity. Okay, so this is all about the total Jahn-Taller distortion. So hope this video will help you a lot in your JAM, NET or GATE examination. Okay, so if you have any query, please comment below, and if you have question that you need to solve, then you can ask me in my on my Facebook group. Okay, you will get the link in the description below. And also, if you want to buy any book, for this I will suggest R.B. Shorter volume 2 and of course the previous one, as I have already said, the Wikiragator. And for this, if you want to buy those books, please buy from my links. You will get the link in my blog, any of my blogs. So check out any of my previous videos. So then go to that blog and just buy from there. So I'll get some commission, and that will actually help me a lot in my study. Okay, so if you want, just tell me. I will definitely make a blog on this topic also, so that you can understand more and more. Okay, so thank you. Thanks for watching.